calculate the variogram for a given domain, we need to first select a domain and select the data within the domain. So to do that, we can go into our domains object, specify the domain name, and retrieve the domain that we are interested in calculating the variogram for. Next, we use domain.getData over all our composites to select only the composites that are within this domain. Let me run this cell. So the result is showing the domain name, the domain code, so that I'm certain that I've selected the correct domain. And also it prints on screen for me the number of data that is inside that domain. One of the first steps in variography is to infer the nugget effect. In this notebook, we are going to infer the nugget effect by calculating a omnidirectional variogram. There are several new tools in this cell, and I'm going to explain each one. In order to calculate a variogram, we need to specify at least two sets of parameters. One is the lag sizes, lag tolerance, number of lags, and the other one is a search, which includes the lags, but also includes some angles and tolerances for variogram calculation. So let's start with the lags. In RMSP, you can specify the lags for variography using the lags class. This class takes three arguments. The first one is the spacing. The second one is the tolerance, and the third one is the number of lags. So in this case, we are specifying two different lags. So starting with lag size of 3 with a tolerance of 1.5 for 3 steps. So that will give us the lag 3, 6, and 9. Then next, we are specifying extra lags at 5 steps and 2.5 tolerance for 6 additional steps. So the final lags that we're calculating in the variogram is going to be a combination of these two, starting with these 3 lags and then appending 6 more. Next, we have the experimental variogram search object. This requires us to specify the angles, the azimuth angle, the inclination angle for variogram calculation. The lag distances are provided by the object that we specified before. Lag tolerance is not required because it's already considered within the lags that we just specified. We can specify azimuth tolerance, inclination tolerance, azimuth bandwidth, inclination bandwidth, and angle tree. For omnidirectional variograms, we relax the angle tolerances. So we are using 90 degrees for azimuth and 90 degrees for inclination. So that means we are pairing every pair in all directions, making a omnidirectional variogram. After specifying the lags and the search, we can calculate the experimental variogram. For the experimental variogram calculation, we use the ExpVario class. For initialization of the class, we need to specify the variogram type. We need to specify if we want or not to standardize the variogram. In this case, it defaults to yes or true. We can specify a CIL for our variogram standardization. We can provide a cutoff, and we can provide a category. The cutoff and categories are only required for specific variogram types. For our application today, we don't need to specify a cutoff or a category. In terms of variogram type, there are many different types that are supported within RMSP. The complete list of all the supported variogram types is provided in the documentation below. In our case, because we're dealing with gold, we are going to be using pairwise relative variogram. Once we initialize the class, we can right away calculate the variogram. For the variogram calculation step, we require the composites, the variable we want to calculate the variogram for, the experimental variogram searches. There are extra arguments that you can pass to this function. You can control the number of parallel threads. You can specify whether or not you want to see a progress bar. And you can provide a normal score transformation table. A normal score transformation table is only required if we used back transform normal score technique for the variogram type. Otherwise, that's not required. Once the variogram is calculated, the output is captured by the ExpVario object. And then we can use that output, which is going to be an instance of this experimental variogram, to plot all the experimental points. And in this case, we are specifying that we want to see the number of pairs bar. So let's take a look at the output. So we calculated the experimental variograms. The first 3 steps are at 3 leg distance, and the remaining points are all at 5 leg distance. The gray bar gives us the number of pairs that were found for each one of the leg calculations. And the right side y-axis is showing the number of pairs that relates to those bars. And on the left side, we have the variogram value. For demonstration purposes, we can retrieve this plot and now switch to tradition. Rerun the variography, and we can compare the results of the two. So you can see that the pairwise relative variogram is way more continuous than the traditional, as expected. Let's go back to the pairwise.